the mass flow rate of stream 3 is going to be the mass flow rate, the total mass flow rate m dot, and we're going to have two different inlets right here, which we've called 6, and on the other side, which we've called 2. We've solved some of this already, so I'm going to put some actual numbers to this. We knew that here pressure 6, right, that's 1 megapascal. We found the enthalpy here, which is 3013.7 kilojoules per kilogram. So we found that on the previous page. And we know from here at 2, again, P2 equals 1 megapascal. And we just found H2, that was 192.81 kilojoules per kilogram. We also know some things from our initial mass balance. If we scroll up to be able to remind ourselves of what we did for our mass balance, we did, right, in equals out, so we had mass balance here. This is what the mass balance, right, 3, 4, and 5 are all going to be the same mass because all of those things are just in and out. Here is where it splits. So we said we have here a certain fraction that's going down 6, and the remainder is going down 7. So the part that went down 7 continues on toward 2, and 6 obviously stays at 6. So let's write what those mass balances are. Six equals y m dot, and 2 equals 1 minus y m dot. We're not quite done yet because we actually were told here P3 obviously is the same, 1 megapascal, and X3, we're told that it's a saturated liquid coming out. So we can look up state 3. Which is going to be at 0 quality and 1 megapascal. And if we look that up, that's 762.8 kilojoules per kilogram. So what we're saying is we're mixing, some amount of 192.8 and some amount of 3,000, and we're ending up with 762. Let's do the actual energy balance to be able to figure that out. So our energy balance here is, I'll write out the whole thing and then we'll simplify it. Equals Q minus W. So we'll simplify this specifically for the feed water heater. So delta H, do we have things flowing in or flowing out? Yes, we do. Do we have big kinetic energy changes? Likely not. Do we have big potential energy changes? Again, likely not. Do we have heat exchange with the surrounding? Likely not. And do we have shaft work? Do we have moving mechanical parts? Also no. So our energy balance, our simplified energy balance is delta H is equal to 0. Let's break that down a little bit more, right? Delta H is, so this is H out minus H in. All of the outs minus all of the ins. So we have a single out, which is H dot 3, and we have two ins, which is 2 and not a plus, a minus, H dot 6. So those are our two ins and our one out, or our two ins and our one out. We can break these apart, right? H dot equals M dot little h. So we can break all of these capital H dots apart into the mass flow rate and their enthalpy. So for example, H3 is M dot 3 times little h3. So this is M dot 3. If we go back up, that was just M dot. So this is M dot times H3, which is 762.8. I'm going to drop units on these enthalpies because all of them will be the same units. Okay, minus M dot 2, which is 1 minus Y M dot, times H2, and 192.81. Now minus Y M dot 13.7 kilojoules per kilogram, and all of that equals 0. We can go through and do the algebra, and this will tell us basically what Y is. We can solve for Y, that's our unknown in this case, right? The M's cancel out, right? So we're going to drop all of the M's because we just divide by M. 0 divided by M is still 0. We can solve for Y algebraically. 762.8 minus 192.81, all divided by 13.7 minus 192.81. So this tells us that Y is equal to 0.202. And it turns out that this is actually our answer to part A. Right. Part A, if we remember back, the fraction of the extraction flow to the feed water heater, 0.202. Right, what that's saying is 20% of our flow rate is being extracted from the turbine and going to the feed water heater. That's what that part of the question is asking. So we figured that out. We just so happens to answer one of the parts of our questions, but we're not done yet. We're going to keep going around our circle, around our flow diagram. So we've now figured out Y, which is great. We're going to continue now. We have 3. We want to go from 3 up to 4. Do that in green. From 3 up to 4. So we're going to go across a second pump. In this pump, we're going from 1 megapascal up to 20 megapascal. So this is pump 2. And this is the process taking us from 3 to 4. We're going to use the same process that we did for our first pump. So we have W minus WP2 is equal to specific volume times delta pressure. Specific volume 3 is 0.001127. So we can figure out the work for this pump minus wp2, 0.001127 meters cubed per kilogram times our change in pressure, which is 20,000 minus 1,000 kilopascals or kilojoules per meters cubed as it happens. So if we go through and do that math, and it's fairly straightforward, this gives us a pump work of 21.41 kilojoules per kilogram. Okay, that's a work value, so we'll box that. This tells us the work. Now we need to go back and do an energy balance to figure out what the enthalpy is. So if you want to, again, just take a minute, go and do that energy balance, and then jump back on the video. We'll see if we get the same answer. So when I do the energy balance, I'm going to skip ahead and just start with this equation, which we're going to continue to use for pumps and turbines. And in this case, right, the outlet is H4, the inlet is H3, out minus in equals minus WP2. And if we want to put values on that, right, we can rearrange that to solve for our unknown H4 equals H3 minus WP2, or H4 equals W3, which was from up here 762.8. Minus a negative 21.41. So H4 is 784.2 kilojoules per kilogram. Again, I'll box that because we're going to be coming back to that later. Okay, go back to our block diagram. We are almost all the way around the circle. So we've gone from 5, we've gone through the condenser, we've done the feed water heater, now we're going our last step across the boiler. So this is from 4 to 5, which is our boiler. Now we've already solved enthalpies on both sides of the boiler, so we don't have to do any extra work to figure out the enthalpy. We can jump straight into looking at the energy balance. So our energy balance, again, I'm going to just jump right into the kind of the meat of the energy balance. If you want to take a minute, go back and solve that and then hop back in the video. Now would be the time to do that. Okay, so I'm going to jump right into the energy balance here and use this simplified form, delta H equals Q. Or in this case, delta H, H5 minus H4 equals Q, which is the specific heat of our specific heat input of our boiler. H5, that was one of the first things we found. That was, if you look back, 4069.8 kilojoules per kilogram. H4 we just found right above, that's 784.2 kilojoules per kilogram. Equals QH, which equals 3285.6 kilojoules per kilogram. We'll box that because we'll need that later. All right, so what we've done a lot, right? But we haven't actually answered all the questions. So we've now gone through and we've gone through our whole cycle. We figured out all the enthalpies. We figured out specific work and specific heat transfer for different things. But we have to actually go through and answer our questions. So we've answered here part A. We now want to answer part B, the total condenser heat transfer rate. So for B, what we're trying to find is this value down here, Q dot L. In order to find Q dot L equals M dot 7, right, the mass flow rate through that piece of equipment times the specific heat transfer rate. If we look at what we found so far, we have found the specific heat transfer rate, QL. Right, we found that, okay, we didn't find that, but we found everything that we need to find that. We found the enthalpy at state 1, we found the enthalpy at state 7. We just have to do a quick energy balance. Right, we know the enthalpy on both sides, so we can find that really quickly. What we haven't found yet is the mass flow rate. To find the mass flow rate, we need to know something about, right, the power. The information that we're given in the problem about power is the total power output of the turbine. So we're going to go back and use the total power output of the turbine in order to find mass flow rate. So we'll go back to turbine, to find M dot. If we look at what our turbine was, I'll just draw a simple diagram here. So this is 5 megawatts. We'll just write it as 5,000 kilowatts. We have an inlet here, which was stream 5. Then we have 2 outlets. The first one, stream 6, goes to the feed water heater, and the second one is stream 7. The mass flow rates that we had a mass flow rate in. We have a mass flow rate which is Y M dot here at 6, where Y was, we just found it 20%. 1 minus Y M dot. Okay, our energy balance for this system is delta H dot equals minus W dot. Okay, delta H dot, that's out minus in. So that is H dot 6 plus H dot 7, our 2 out streams, minus our in stream, which is H5 that's equal to negative 5,000 kilowatts. Now we simply have to plug in what these are. So this is m dot 6 h6 plus m dot 7 h7 minus m dot 5 h5 equals minus 5,000 kilowatts. Okay, we've already figured out what all of these different mass flow rates are, at least as in relation to each other. So this is, I'll plug in numbers because we know y is 0.202. So we can just plug in some numbers for this, and this is 0.202 times total mass flow rate times 13.7 kilojoules per kilogram. We'll add those units. This is kilojoules per kilogram plus 0.798, 1 minus y, m dot 2235.1 kilojoules per kilogram. Right, that's H7. And then we'll jump down onto the, right, I'll write some ellipses. We'll jump down on the bottom line. Mass flow rate 5 is just m dot. The enthalpy of 5 is 4069.8 kilojoules per kilogram, and that equaled 5,000 kilowatts or kilojoules per second. So we can go through and solve this, and if you do, you'll find that the mass flow rate is 2.98 kilograms per second. Okay, so that is the mass flow rate through our system. We are getting there. So now for part B, now we actually can answer it. So we were looking, B asked us to find Q dot L, which we said equals m dot 7 times QL. So let's find what both of these values are. We can find QL from an energy balance. Right? We're doing lots of energy balances, clearly. Our energy balance is our energy balance across the condenser. Let's go back up and look at our picture to see what that is going to be. The energy balance is the energy balance across the condenser here at the bottom, where we have energy coming in at 7 and leaving at 1 and QL. So we don't have any work, we don't have any kinetic energy or potential energy changes, so our energy balance is just delta H, say delta H dot equals Q dot. That's our general, or that's our simplified form of the energy balance, which is going to be out minus in. So coming out of our condenser, we have H1. Coming into our condenser, we have H7. wk7, and Q, we have Q dot L. So we can find this where Q dot L is equal to H1, which is going to be the mass flow rate of 1, which is 0.798 times 2.98 kilograms per second. Right, this whole value, this is 1 minus y m dot. Right, or m dot 1 times now the specific enthalpy of stream 1, which if we go back up and look at our work from before, okay, the specific enthalpy of stream 1, we have to go back a little ways, it was 191.81. So this is 191.81 kilojoules per kilogram, minus, same thing, 0.798, 2.98 kilograms per second. And now our enthalpy is enthalpy 7. So if we look up here, was 2235.1 kilojoules per kilogram. If we plug this in, we can find that the heat transfer rate QL through the condenser is 4858 kilowatts. Okay, now last but not least, part C, we're asked to find the thermal efficiency of the cycle. The thermal efficiency is defined as the net work out divided by the heat input. So the heat input is fairly straightforward. There's only one place where we're putting heat into the system, and that's QH. So that equals the heat input of our boiler, the specific heat of our boiler, times the mass flow rate. So let's go back up. We found right here the specific heat input of our boiler, 3285.6. So the total heat rate is that times the mass flow rate. So the mass flow rate, 2.98 kilograms per second, times that specific heat transfer, which is 3285.6 kilojoules per kilogram. That gives us a total heat rate in the boiler of about 9790 kilowatts. Next, we need to find the net work. The net work output is the sum of all of the work terms. That's W dot P2. Understanding that the sign has to work out so that our turbine's work is positive and we're subtracting off the work that we had to put into the pumps, because that's work that we had to put in, not work that we're getting out. So our net work, W dot net, is equal to 5,000 kilowatts. That's the work of our turbine, plus the work of our first pump, which is the flow rate through that first pump, 0.798 times 2.98 kilograms per second. That's the mass flow rate, times the specific work, which is negative 1.0 kilojoules per kilogram. So that's W dot P1. And then a similar thing for the second pump, which is, again, the mass flow rate through that is 2.98 kilograms per second, times the specific work of that, which is minus 21.41 kilojoules per kilogram. So our first pump and our second pump. Right, this is, just for clarity, I'll write, we'll use a different color, W dot net. This is W dot T plus W dot P1 plus this is M dot WP2. Not Y, that's 1 minus Y. Okay. If we go through and plug in the actual numbers, the work that we're putting into pump 1 is about 2.4 kilowatts. The work that we're putting in here at pump 2 is about 64 kilowatts, so significantly more. But our net work out is 49.34 kilowatts. That means our thermal efficiency, right, how well we're using the heat that we're putting in, we're getting out 49.34 kilowatts, but we had to put into our boiler 9790 kilowatts of heat. So our overall thermal efficiency is 0.504. And that would be the answer to part C. So hopefully this gives you a little bit of practice, and at least practice thinking through how we go about solving these problems, how we can look at them. Hopefully you were able to stick with me for the full, 5 pages and a full hour of me talking. But I do hope it helps show how kind of thinking through these in an ordered step-by-step process, how that can help us solve even relatively complicated problems such as this without having to do anything really too fancy as far as the solution. We just have to make sure we continue to look at this in an ordered and step-by-step manner.